Hey kids, let's do some tangent planes, right? Instead of tangent lines. So recall another branch off from Calc 1 that we talked about differentiability and locally linear, right? Do you remember that? So graphically, when you're looking at a graph, when do you expect the slopes from the left not to equal the slopes from the right? Corners, right? In two-dimension, we talked about a corner, like absolute value. Right? Remember, a function is locally linear if the function behaves like its tangent line at every point in its domain. So absolute value is not differentiable because no matter how far you zoom in on that sharp point, it will never straighten out and look like a line, right? And you can kind of sort of think of, right, the slopes from the left are constantly -1, and the slopes from the right are constantly +1, and they come screaming in towards one another, and the slopes do not gradually approach any number. Kind of have the same thing as a cusp, right? A cusp, right? You come, right? The slopes from the left are all negative. The slopes from the right are all positive. And again, I have this sharp point where I can't really draw a unique tangent line. Then I do have a kind of a smooth curve, but here I don't have a sharp point, but the slopes are approaching at 0, a vertical tangent. I can draw a unique tangent line there. It's just vertical. So we say that absolute value is not locally linear, that x to the 2/3 is not locally linear. Actually, the cube root of x is locally linear, but neither one of them are different. None of these are differentiable, right? So vertical tangency is kind of this oddball case where I can zoom in and my function looks like its tangent line. It's just that my tangent line there, its slope is numerically undefined. A function is differentiable if its derivative exists at every point in the domain, right? So derivative doesn't exist at a corner, derivative doesn't exist at a cusp, derivative doesn't exist here simply because I have a vertical tangent. And then of course, when I have discontinuities, right? If I have discontinuities, of course, a derivative does not exist here at 0, at x equals 0, I don't have a derivative. So we need to take this idea into 3 space and talk about when my 3 space is differentiable. I forgot I had duh there. So firstly, if there's a theorem, now I don't ever need to test you on this theorem, but there's going to be some homework problems where you need to use this theorem. If I ask, show that a certain function in terms of xy is differentiable, you need to look at the partial x in terms of with respect to x, partial derivative with respect to x, partial derivative with respect to y, and just show that they exist. Then also show that they are continuous. That is enough by a theorem, right? There's certainly a proof behind this, that the function f is differentiable at the point in question. At the point in question, right? I didn't say differentiable everywhere. We are going to be interested in a point of tangency. So if I have a surface in my 3D space, and I do have my first partial derivatives exist and are continuous, then all the tangent lines at a given point to that surface form a plane. And instead of calling that a tangent line, we call it a tangent plane. Now I'm going to do a pathetic drawing, right? No judging. There's my 3D surface, and I have some plane up there, right? My domain is xy, and z, the function, I do something to x and y, and I get some surface up here in 3D. And let's say that there is a point. That point, I inputted an x, I inputted a y, and it generated a z by applying the function, right? Well, there is, right? What if I take a line that is tangent, so imagine, right, this line is tangent to that curve at the point of tangency. And then I have another line, let's say. I don't know why my pen is so terrible here that I can't draw a nice line. Another point of tangency. Let's call this, another line that goes through the point of tangency. Let's call that tangent 1. And let's call this one tangent 2. Right? There is a plane that contains those two lines. That is called a tangent plane. Right? And there's a whole bunch of points, obviously, a whole bunch of tangent lines, obviously. But even if I just picture two of them, and again, I know that is a terrible, terrible drawing. I will try to do better. I have some GeoGebra to show you. But if that point is a point on the surface, x naught, y naught, z naught is a point on the surface created by plugging in the domain x's and y's into a function and generating the z value, the tangent plane has an equation. Now, you know what equations of planes look like. That's not that useful to us. That's in general. Now, notice I did, though, put the point of tangency in there. Right? X, y, and z, x sub naught, y sub naught, and z sub naught, is the coordinates of the point of tangency. Now I'm going to do a little algebra. Can you imagine that I moved these two terms over here and divided everybody by c? So wouldn't I get negative a over c on this side? And then I would only have z minus the z coordinate over here on the right side. Yes? Are you with me with that algebra? I'm going to call this and this question mark 1 and question mark 2, the multipliers on x minus x sub naught and y minus y sub naught. If you think about holding the, let me write this a little bit better then. So I have z minus z naught is equal to this weird thing. Don't know what this is, that whole negative b over c thing. And this idea that we used yesterday of in previous lessons about what if I hold the y value to be constant, right? In other words, I plug in for y sub 0, and I don't let it change. What happens to this term? That term goes away, doesn't it? And then do you recognize this? Maybe you'll recognize it like this. What does that look like? Sure does. Point slope form of a line, right? What goes here? The slope. What do you think the slope in our multi-dimension, right, comes from a D word? Slope goes with the D word, derivative, but this is, I held y constant, so this is going to be the partial derivative with respect to x. Can you see what, if I would do the same thing for holding x constant, what would happen? Right, if I went up to this blue equation and I held x constant, this term would go away and I'd just be left with another version of point slope form. So look at what I have here. I don't actually like the way, this is how your book writes it. I don't actually like to put this x sub 0, y sub 0 here, or x naught, y naught. I prefer to just say partial x, right? Because what this means is the partial x, the partial derivative with respect to x at the xy of the point of tangency, right? Evaluating the partial derivative at that point in the domain, evaluating the partial derivative of y at the point, right? The domain points, x0, y0, x naught, y naught. And then my z's are over here. So what is that doing, right? That is taking, right? If you have some surface and you have a point P on there, you just found the equation of that tangent plane. And remember the whole idea of zooming in Calc 1, zoom in on a curve as long as it's differentiable and it looks like its tangent line. Well, guess what's true here? If you zoom in close enough on this shape, it will appear like it's tangent plane. Let's do an example. What if I gave you the surface? So z equals a function in terms of x, y, and I tell you that z is equal to 2x squared plus y squared, and the point I care about is 1, 1, 3. Okay. I want the equation of the tangent plane. Well, first I need to look at the partial derivatives. So partial x evaluated at the domain values, right, in 2 space. So partial x evaluated at 1, 1, holding y constant. I just get 4x, plug in the point. It's only dependent upon x, so I just get 4. How about the partial y at the point 1, 1? Go up here. I just get 2y. So fill in this equation, right? Z minus the z coordinate of the point of tangency, which is 3. If I got that in standard form, it would look like this. Or I guess you could even do this. Right? Let's take a look at that. The equation of its tangent plane. So do you recognize what this is? Do you know, you can tell what this is, right? Right, an elliptical paraboloid. There it is, right? 2x squared plus y squared, and here's the point 1, 1, 3, right? Because when you put 1 in, 2 times 1 squared plus 1 squared is 3. So down here, the point 1, 1, 1, 1, the function takes it up here to a height of 3. Here's the equation of the plane that we just found. Right, see the plane? And look what happens as we zoom in, right? That elliptical paraboloid starts to look like its tangent plane. Cool, right? So again, if you zoom in close enough, as long as you are differentiable, the surface looks like it's tangent plane. And remember with our, what was our partial derivatives? 4x and 2y are certainly, they certainly exist at and are continuous at the point 1, 1. Next, oh, so this is what I was just showing you, that if I, oh, where'd it go? Right, what happens to the equation? Sorry. Right, there's the equation of the tangent line to the curve in the constant plane where y is constantly held as the y coordinate of the point of tangency. Here's if you hold x constant, what happens to the equation? It looks like just your point slope form. Remember, this notation is not parent. This means the partial derivative of y evaluated at x naught, y naught. And I kind of have these two lines in this next applet. This one's a little more complicated surface, but if you look at it, right, I have a tangent plane going, there's a point of tangency. Here's my point of tangency right here. There's my tangent plane at this point, and I have two intersecting tangent lines going through it. Right. Right in there, if I move, right, holding one constant versus the other constant. There, they're both moving. Kind of cool, right? There's the perpendicular plane. I have to say, I do like my GeoGebra. All right. Now, just like in Calc 1, we learned how to write the equation of a tangent line to a function, and then we learned how to use that tangent line to approximate a curve. We're going to do the exact same thing. We are going to use our tangent plane to approximate those values of z. So the linearization of a function in two variables looks like this. Now let's piece this apart. Let's take this apart a little bit, right? Remember what we had before? Our equation looked like this. Right? So this equation, right, the linearization of the function is equal to, look at what this is. What is that? That's just z sub 0, isn't it? If you take the function and you plug in the given x and y, well, you get the z coordinate. So if I plug in x naught, y naught, I'm going to get z naught, right? So all I did was move this over here, so it's positive. Z, remember, z is equal to f of xy. So I'm saying the linearization of xy is equal to the z coordinate plus point, slope, point, slope. The approximation is f of my actual surface, my actual value for z, right? This is actually z. Z is equal to f of xy, which is approximately my linearization equation. The linear approximation or the tangent plane approximation of my function at x naught, y naught. And remember, you get z by operating upon x and y. So I'll save a couple of examples for when we're in our live session, but I wanted to do this one with you because this one asks you about the theorem without asking you to write out anything about the theorem. When it says explain why f of xy is differentiable at a point, right? It doesn't say differentiable everywhere. It says differentiable at a point. Find the differential, the partial derivative with respect to x at 2, 1, and the differential of y at the point 2, 1. So what is my, I have a quotient here, right? So remember though that y is a constant, right? So this is like x over x plus 4. So what is my derivative? The bottom, right? We do high over ho. So it is ho d high minus high d ho, right? The derivative of x plus a constant is just 1 all over x plus y squared. So what do I have here? X plus y minus x, so that just is y over x plus y squared. What is that at 2, 1? So the derivative exists at 2, 1 and is continuous at 2, 1. How about this one? Still going to do high over ho, the quotient rule. This time x is constant, right? So it is the bottom times the derivative of a constant, which is just 0, minus the top, high, times the derivative of the bottom when x is a constant. So the derivative of y is just 1, all over x plus y squared. So I end up with negative x over x plus y squared. Look at that at the point 2, 1. So both derivatives exist at 2, 1, and then go up here to the actual function at 2, 1, and I get 2 over 3, therefore continuous. So if the function is continuous at the point 2, 1, and the partial derivatives exist at the point 2, 1, then I am differentiable, right? So that's all I want for explain differentiable. I want to see the derivatives and that you say both the derivatives exist. And I want to see that you plugged into the function and tell me the function is continuous there, right? And you can see obviously that the only place I'm going to have issues is when x and y are 0. So 2, 1 is fine. Tell me those things, therefore differentiable. Okay, so I've done the first part, check. Now find the linearization, which just means write the equation of the tangent plane. So to show differentiable, partials exist, function continuous at point. Find the linearization. Write the equation of the tangent plane. Use the linearization okay, so we did 1. Now let's do 2. Z is approximately two-thirds, which I got up here, right? F of 2, 1, plus those derivatives that I erased. What was it? Oh, it was 1/9 x minus 2, and then negative 2/9, right? X minus 1. And I could, right? Nobody told me a form to leave it in, so I can just leave it that way, right? If you want to expand and combine, or you need to match multiple choice, fine. But z of, as long as I am close to 2 and close to 1, this tangent plane is a good approximator. So z of 1.9 comma 1.1 is approximately L of 1.9 and 1.1, which just means I'm plugging in right 1.9 and again, hopefully you can see that the change in there is very small, which is what you want, right? Delta x is small, delta y is small, right? And then whatever that turns out to be, blah, blah, blah. Actually, let me figure out what that is, right? Let me pull out my calculator because then I want to plug into the original. So if I have 2 divided by 3, excuse me while I push buttons on my calculator. So I got 0.6333 repeating. So I do have the function. What is z of 1.1, 1.9 comma 1.1?
No.
Oh my goodness, I got 0.633 repeating, right? So this was a pretty darn good approximator. All right, so we'll do a couple of examples in our live session, a couple of other examples to practice this, but hopefully you really do see the link between what we're doing with tangent planes and using tangent planes as an approximator to a curve in 3 space and what we did in Calc 1. All right, I will see you later.